welcome back, and welcome to Depth First Search. So we've just had a look at Breadth First Search, which is the other algorithm I think everyone under the sun knows, where we're searching radially across at each level at a time. Depth First Search, the strategy again is going to be the order in which we expand nodes. Depth First is going to go down deep dives, one at a time, all the way down as far as possible at every point. So essentially, we're going by depth. We want to increase the depth, if possible, every time we're expanding a node. So if I rewrite this again, the strategy of Depth First Search is we're going to expand nodes recursively by a depth downwards. So we're going to do this all the way until we can't go further down, or we actually discover that we've found the goal, or found a goal. So as opposed to Breadth First Search, which is first in, first out, we could describe this in terms of a queue as last in, first out, LIFO. So let's have a look at this. So similar to before, we have the open list. It begins very, very simply. Only the root node is in it. So similar to Breadth First Search, Depth First Search DFS is going to, of course, expand A first. The root node has to be popped out of the open. And now we generate two children. When we expand A, we find again both B and C. Now, again, both B and C have the same depth 1. They both look exactly the same, so which one is first is up to tie breaking. I'm now going to just vary it up slightly then. So I'll put in C before B. But again, up to tie breaking either way works. Now, this is the difference between DFS and BFS. We are last in, first out. Great, B this time was the last node into the queue. It's the first one out. We're going to pop a B first. So when we jump back in, we're expanding B. It's going to generate, again, two children. So in the open list, C is still in the open list. Happy days. Now we're adding both D and E. The order we add them would be tie breaking once again. I'll put them in as E, D. Ta-da. So in this case, we would then next expand D. Either we'd continue downwards and recursively do this. Let's say that this is the bottom. This is now a dead end, okay? So we've expanded D, nothing happened. We've left with a C, E. What we're gonna do is we're gonna pop E, expand E, find the same thing. It's still a dead end. We finally now return up to C. See how the difference now is we've explored downwards in the tree before coming back up to the other subtree over on the right-hand side. Finally, we expand C. This is now when we generate the remaining nodes, F and G. Again, you could put them in either order. Let's say this time instead it's FG. Great, then we'd pop out G and we'd find it. In this case, again, I'm going to just say, let's pretend that G is the goal node, aptly named, and we would get to stop actually before we never even have to look and expand F. So this is DFS. DFS is also extremely simple. I think it's very intuitive, easy to understand. But now what will be quite interesting is let's compare then the properties of DFS. And we'll now have a good comparison point against BFS, which we've already seen. So we're going to talk about these again in terms of the completeness, optimality, and then time and space complexity. Yep, space complexity. Okay, so this one might be a little bit different. Let's talk about the completeness, okay? So as an example in this, let's consider again G as our goal. When you're thinking about completeness, we need to consider all possible versions of where the goal could be. You're kind of trying to think of, I guess, worst case. But in this case, this is going to be the worst case. So in the graph that I saw, where D, E, F are dead ends, what's going to happen is that even though we go down the left side of the subtree first, we will eventually find G, as we've done here. Therefore, that search was able to find the solution. That is not always the case. So let's talk about why. The difference here is what happens when the tree grows downwards infinitely. So it can absolutely be the case, say in a maze, right? If we have some form of strategy of expanding where we try to go left every single time, right? That might be the first node that's generated every time. It's a decision of left or right in some form of maze. However it is, it doesn't matter what the actual problem is, but it can be the case that we can enter cycles, or the problem's just large enough that this can decrease an infinite amount. In both of these situations, DFS does not guarantee that we will ever arrive in the right subtree at all. And so because of this, is it complete? No. There are situations that it cannot find the solution even though one exists. So that is extremely problematic for our algorithm, right? And all of a sudden now defining these types of properties really does inform us greatly about the different trade-offs we're making. There are some advantages though to DFS that we'll have to talk about when we start comparing these more closely. Now, optimality, does it guarantee when it finds a solution that the solution is optimal? The answer here is also no. So similarly before where I wrote like G2 as another goal, imagine there was another goal all the way at the end here, okay? G2 can be found, it will be found before this guy because we're progressing downwards by depth. G2 has a substantially worse cost. Again, there's like an asterisk, is the cost related to depth? In the case that it is, and we're happy, even with a uniform cost, this is the worst solution, right? So no, we cannot guarantee that the solution will be optimal. So now when we're trying to discuss the time and space complexity for DFS, what's important is that we're actually going to need to introduce a new term. So previously for BFS, we're able to describe it quite succinctly in terms of the branching factor B, as well as the depth of the solution, D. Unfortunately, in DFS, we have very different behavior, right? Despite the fact that, let's say, the goal is at this node G over here, the actual amount of space and time that the algorithm's going to take is dependent on a new factor, which we're going to call M. So M is what is going to be the length of the longest branch. Okay, so why is this important? Well, essentially, despite the fact that the depth of the solution might be rather shallow, here, depth first search is going to expand downwards as far as it can go. We're going to say it's doing this left first traversal, right? This path can go down very, very far. How far it goes down is the distance that we're going to call M, right? This is the deepest branch, the longest branch. It's essentially the maximum depth of the tree itself rather than the depth of the solution, which we've been talking about as D. So why is this important? Well, M can be dangerous. So if you have cycles in your graph, as well as some problems, simply if you have some form of null operator or you're allowed to return to the same location, what can happen is that the trees, the search tree, can grow infinitely downwards. And so in both of these cases, M may be infinite, which means that we would never actually be able to get back to G. So we've talked about that in terms of the completeness and optimality. But here, yeah, so M is essentially, right, like the length of the longest branch, and this can be substantially larger than D. We don't know how far down it can go, and even in finite trees, say there is some maximum depth, M is often larger than D. So this is really important for informing our discussion. Okay, so now with M defined, we can return to the space and time complexity for DFS. Instead of having to explore at every branch, right, there's B decisions you can make, and it will go to the power of however far the depth of the solution was. So that was for BFS, right? And then we would have O of B to the D. The difference here is that we may have to expand, right, the branching decisions all the way down to however far M belongs. And so that is what is informing our time complexity here. So it is O of B to the M rather than D. And again, M can often be much larger than D. So that's important. However, with the space complexity, this is a bit interesting. So, hey, it could be O of B to the M similarly if we didn't do some fancy tricks. We'll talk about it in another video. But depth first search is actually quite an interesting algorithm because we can drastically reduce the space required for search simply by actually not needing to remember a lot of the paths. So at some point down, when you get to a node and it has no children, you can, once you've exhausted its children, there's no need to ever keep that node in your memory. You can just chuck it away. Because we've gone as far down as you could possibly be, right? And then that can recursively happen as we backtrack, which means you're throwing away more and more of the search tree. What this means then, actually, for space complexity, is we end up with O of Bm. So the only number of nodes we might actually need to keep and track is essentially the branching factor times the maximum depth of the tree M. So we'll explore that and justify that in a later video. So we've seen that BFS and DFS have some similarities, but also have some very stark differences in terms of the properties they offer. So in the following videos, we'll then come back and start comparing and figuring out why we would use one algorithm over the other. But we see that essentially BFS has better guarantees in the sense of completeness and optimality, simply due to depth first search's danger of proceeding unbounded down some M, right? So if M is unbounded, we run into significant issues in terms of completeness and optimality, as well as, I guess, the complexities here, basically based on whether or not M is bounded. Okay, so if we have an infinite recursion, there could be a cycle in the actual original problem, right? Imagine you start spiraling around an obstacle. In these situations, we get really, really, really bad behavior, and we may never terminate, okay? So, yeah. Despite that, we see, there are some similarities between breadth first search and DFS, but also there are these really, really stark differences that lead to very different behaviors and problematic behaviors. So in the following videos, we will compare these a little bit more and talk about actually why we would use DFS in some situations and what are the strengths and advantages of both. So see you there.